Steel is the most recycled material on the planet. Today, more than half of all steel produced worldwide no longer comes from mined iron ore, but from scrap. Discarded metal that once belonged to cars, buildings, ships, machinery, and even household appliances. This shift does more than reduce mining. It saves up to 70% of the energy required to produce new steel. It is no exaggeration to say that recycling has become the backbone of modern metallurgy.
But what really happens to rusty cars, demolished structures, or abandoned industrial machines? How does lifeless debris get reborn as brand new steel, ready to build the future once again? In this documentary, you will witness that transformation from towering mountains of scrap metal to a molten, glowing river of steel. A material that can be recycled infinitely without losing quality. A metal that carries the weight of entire civilizations.
Before we begin, don't forget to subscribe and enable notifications so you don't miss the next episode where we explore the industries that keep our world moving. Subscribe for more deep dive documentaries on how our world is engineered. 1. Steel, the most recycled material on Earth. Every year, more than 660 million tons of steel scrap are returned to the furnace. This number is greater than the combined total of recycled aluminum, copper, plastics, and glass. Steel's ability to be melted and reborn endlessly, without degradation, is what makes it the backbone of global infrastructure, transportation, machinery, and energy systems. But its environmental benefits are just as astonishing. Recycling just 1 ton of steel saves over 100 kilos of iron ore, 635 kilos of coal, 54 kilos of limestone, and cuts CO2 emissions by almost 60%. In a world urgently trying to reduce emissions and energy consumption, steel recycling has become not just an economic solution, but an environmental necessity. The recycling chain begins long before the material reaches a furnace. Scrap steel comes from countless sources. Excess metal from manufacturing, beams and columns removed from construction, end-of-life vehicles, demolished bridges, decommissioned ships, industrial machinery, and appliances such as washing machines and refrigerators. According to the Bureau of International Recycling, nearly 60% of all recycled steel worldwide comes from end-of-life products. This means that the very objects society discards today become the raw material of tomorrow. Once scrap is collected, it is loaded onto specialized trucks, rail cars, or containers and transported to massive scrap yards. Some of these sites can hold tens of thousands of tons at a time. In the United States, such yards are often known as steel banks, logistical hubs capable of receiving thousands of truckloads per day from cities, industrial parks, and seaports. Thanks to this system, more than 70% of U.S. steel production today comes from scrap. Brazil follows a similar path. Roughly 70% of its national steel output originates from recycled scrap, making it one of the largest steel recyclers in Latin America. Not all scrap is equal. Heavy industry steel, like the metal from bridges, rail tracks, or ships, is usually clean and contains fewer impurities. In contrast, steel from appliances contains coatings, plastics, or alloyed components that must be removed carefully. For this reason, scrap yards in the US, Europe, and Brazil enforce strict impurity limits on the material they receive. Every load is inspected, every batch is classified. Once sorted, scrap is either compressed into dense blocks or grouped into standardized packages. This reduces transportation costs and stabilizes quality, saving the global steel industry millions of tons of raw minerals every year. Some scrap is too large to be fed directly into a furnace. Cars, shipping containers, industrial machinery, refrigerators, these bulky objects must first be reduced. Enter the hydraulic press. In gigantic scrapyards, powerful presses capable of exerting thousands of tons of force flatten vehicles in minutes. An entire car, its frame, panels, and engine block is crushed into a compact steel cube. The goal is simple: reduce volume, maximize transport capacity, and create furnace-ready metal blocks. This uniformity allows electric arc furnaces and blast furnaces to operate more efficiently. Many countries standardize block dimensions to ensure consistency throughout the supply chain. Thanks to this step, even once impossible scrap becomes manageable raw material. After compression, scrap enters the shredding line, a colossal machine capable of devouring hundreds of tons of metal per hour. Inside a reinforced steel chamber, a massive shaft equipped with hardened alloy hammers rotates at thousands of revolutions per minute. Under relentless impact, cars, refrigerators, containers, and beams are ripped into fragments the size of a fist. But shredding is only half the story. The real magic is in what comes next: separation. Powerful magnets pull ferrous metals from the shredded mix. Plastics, rubber, and glass are removed using air jets, vibrating screens, gravity separators, and eddy current sensors for non-ferrous metals like aluminum or copper. Modern shredders go even further. Optical sensors and X-ray analyzers can identify the chemical composition of each fragment. Carbon steel, stainless steel, and special alloys are separated automatically, long before they reach the furnace. A single shredding line can turn hundreds of end-of-life cars into pristine steel feedstock in just a few hours. Automation is powerful, but imperfect. That is why human sorting remains essential. Workers stand along conveyor belts, removing wood, plastics, rubber, and any remaining non-metallic objects. This careful intervention prevents furnace contamination and ensures higher consistency in the recycled steel feedstock. Shredding and sorting dramatically reduce storage needs, improve furnace efficiency, and guarantee a stable, predictable material flow. Uniform, low-impurity scrap melts faster, consumes less energy, and yields cleaner, more precise steel. For many metallurgists, this step is the first major quality filter, the foundation for every ton of recycled steel produced. Leather is one of the most iconic and durable materials ever created by human hands. It shapes our footwear, protects our tools, elevates fashion, and even supports the interiors of luxury cars and aircraft. But behind every leather product, whether a simple belt or a premium handbag, lies a long, intricate, and highly specialized industrial journey. Today, you're about to discover how raw cowhide is transformed into the luxury leather goods that fuel a global market worth more than $100 billion every single year. From cattle farms to state-of-the-art tanneries, and finally to manufacturing lines where craftsmanship meets mechanical precision. We'll explore each stage in detail. If you enjoy videos like this, don't forget to subscribe and turn on notifications so you never miss another deep dive into the world of industrial manufacturing. The story of leather starts long before the hide reaches a factory. Leather production begins on cattle farms located across the world, particularly in countries known for large-scale beef production such as Brazil, the United States, Australia, and several nations in Europe. Although many people assume the leather industry drives cattle farming, the reality is that leather is actually a byproduct of the meat and dairy industries. Instead of being discarded, hides are collected, preserved, and turned into valuable materials. In many regions, cattle are raised under highly controlled conditions. Farmers monitor genetics, nutrition, and environmental factors that affect hide quality. For luxury leather, the condition of the animal's skin is everything. Scar-free, uniform hides fetch the highest value. Once the animals are processed for food, the hides are quickly removed and treated to prevent decomposition. This early preservation step is crucial because cowhide begins to break down within hours if not properly handled. Fresh hides contain roughly 60% water and are extremely susceptible to bacteria. To stop deterioration, they must be stabilized immediately. There are three major preservation methods. Wet salting. The hide is completely covered in salt, which draws out moisture and inhibits bacterial growth. This is the most common method worldwide. Brine curing. The hide is soaked in tanks filled with concentrated salt water. This method ensures deeper penetration of salt in less time. Air drying used in hot, arid regions. The hide is stretched and dried in open-air conditions until hardened. Depending on how the hide will be used, whether for car seats, shoes, fashion handbags, or industrial applications, the preservation method may vary. At this point, hides can be transported safely around the world. Major tanneries buy raw materials from global suppliers, processing them into specialized types of leather that meet the demands of different sectors. Once the preserved hides reach a tannery, they undergo a meticulous inspection. Workers and advanced scanning systems analyze the hides for thickness, visible scars, holes or defects, brand marks overall surface quality. Next comes sorting. Hides are classified not only by quality, but also by size region of origin. Preservation method intended market high-grade hides may be destined for luxury goods, while medium and lower grades may be used for shoes, furniture, or industrial applications. 4. Rehydration, bringing the hide back to life. Salted hides are stiff and rigid when they arrive at the tannery. To prepare them for processing, they are soaked in huge drums filled with clean water. This step can take anywhere from several hours to more than a full day, depending on preservation method and thickness. During rehydration, salt is washed away, dirt and debris are removed. The hide regains flexibility. Enzymes and chemicals help restore natural moisture levels. The goal is to bring the hide back to a state that closely resembles its original fresh condition. The next major step is liming, one of the most critical phases in leather making. The hides are placed in rotating drums with a solution of lime and sodium sulfide. This mixture removes hair, breaks down unwanted proteins, loosens fibers, swells the hide, removes fats and natural oils. Liming is essential for opening up the collagen structure, which allows tanning agents to penetrate deeply later on. After liming, the hide becomes significantly thicker and swollen, giving it the texture of firm rubber. Once limed, machines begin the process of mechanical shaping. Fleshing machines. Powerful blades remove excess fat and tissue from the inner side of the hide. Splitting machines. The hide is cut horizontally. The top layer becomes grain leather, which is the highest quality. The bottom layer creates split leather, used for suede or lower-cost products. Different industries require different thicknesses. Automotive leather, for example, must be extremely consistent. Until this stage, the hide is swollen and alkaline due to the lime. Now workers must reverse that process. Deliming removes excess lime using mild acids. Bating uses enzymes to soften the hide further. This step creates the supple texture associated with high-quality leather. Bating is especially important for fashion and luxury goods. Stiffer hides would never achieve the flexibility needed for fine stitching or shaping. Tanning is the heart of leather production. It transforms organic hide into a durable, water-resistant, rot-proof material. There are several major tanning methods. Chrome tanning, most popular worldwide, uses chromium salts, produces soft, flexible leather fast and efficient, ideal for clothing, car seats, shoes. About 80% of all leather today is chrome tanned. Vegetable tanning uses natural tannins from tree bark and plants, takes weeks instead of hours, produces firm, traditional leather used for belts, saddles, artisanal goods, synthetic and aldehyde tanning, used for special applications, offers unique colors and heat resistance. After tanning, the hide is now officially leather. It no longer decomposes and can last decades. To achieve the right look and feel, leather undergoes several finishing processes. Retanning for improved structure neutralization to balance pH dyeing using vibrant or natural tones, fat liquoring, which adds oils to soften the leather. Dyeing drums allow color to penetrate deeply, so the leather remains uniform even when stretched or scratched. After coloring, leather is carefully dried using one or more methods. Vacuum drying, toggle drying, stretching the leather on frames, high temperature tunnels. The drying method affects texture, softness, and overall quality. Once dried, the leather may be staked, beaten and softened using mechanical arms to make it smoother and more flexible. This step determines the final look of the product. Finishes can include protective coatings, embossing patterns like crocodile or pebble grain, polishing glazing matte or glossy effects. Luxury brands demand precise textures and colors, so tanneries often create customized finishes tailored to each client. Now the leather leaves the tannery and moves to manufacturing facilities. Here, skilled artisans and precision machinery transform it into handbags, shoes, wallets, car interiors, jackets, furniture upholstery, heavy industrial gear. Teams analyze grain direction, softness, and durability before cutting. High-end brands may discard up to 40% of a hide to maintain perfect consistency. Every stitch, fold, and edge must meet strict quality standards, especially for premium goods. Finished leather goods enter the global supply chain, reaching fashion houses, automotive companies, furniture manufacturers, high-end boutiques. The value added through branding, design, and craftsmanship can multiply the price dramatically. A hide worth $60 at the tannery may eventually become a $4,000 handbag. If you're enjoying this deep dive, make sure to like this video. It helps the channel grow. Want to explore more industrial processes? Subscribe and turn on notifications so you don't miss the next episode. Comment below which factory or industrial process you want to see next.